Welcome to this week's first lecture. In this lecture, we are going to be considering inverse Laplace transformation. Remember, in the last lecture, we have seen how we can take Laplace transformation, and in today's lecture, we are going to see how to invert the Laplace transformation. So by looking at the Laplace transformations, functions of S, we are going to see how we can obtain the time function. And as a result of this ability, you're going to be able to see a Laplace transformation, and then you will be able to see, you will be able to tell what type of time function it represents. So today's lecture is about taking inverse Laplace transformations. I'm going to start with a simple example, and then you're going to see what type of procedure we are going to use. So we have seen some simple Laplace transforms like 1 over s or 1 over s plus 1, etc. But of course, the Laplace transforms that we're going to be working with will be much more complicated than those simple examples. So let us start with an example of that type. So we're given the f of s as s plus 1 over s squared plus 2s. So in the last lecture, we have seen some simple examples, and this one is looking like none of those. So what type of examples we have seen? We have seen, for example, one which had the Laplace transform, which is the unit step function having Laplace transform 1 over s. Or we have seen t, which is the unit ramp function with the Laplace transformation 1 over s squared. We have seen an exponential function e to the at. This has a Laplace transformation 1 over s minus a. And you see that this Laplace transformation does not look like any of those. And of course, we have seen sine omega t and cosine omega t. So this was omega over s squared plus omega squared. And cosine omega t was s over s squared plus omega squared. So we see that there is some resemblance of that function with this cosine and sine, but this resemblance is not exact. So I have an s squared here. In the sine and cosine, we have again s squared in the denominator. But here, this coefficient, the second coefficient in the sine and cosine should be a constant with respect to s. But the second coefficient in this Laplace transformation is dependent on s. Therefore, I see that this Laplace transformation does not look like sine or cosine either. So the procedure that we are going to be following in order to be able to take the inverse Laplace transformation is going to be to look at the poles of that Laplace transformation. Remember, zeros are the roots of the numerator polynomial and poles are the roots of the denominator polynomial. And in order to be able to look at the poles, I'm going to find the roots of the denominator polynomial. So we see here that this denominator polynomial is nothing but this. If I take s parentheses, it is going to be s times s plus 2. So where are the poles of this Laplace transformation? So the poles, if I make a pole zero map for this function, then it's going to be looking like this. There will be a pole at s equals to 0, and there will be a pole at s equals to minus 2. Okay? And there will be a 0 at s equals to minus 1. All right? And what is going to be important for taking the inverse Laplace transformation is going to be the poles of the Laplace transformation. So here, by concentrating on only the poles of the Laplace transformation, I will be able to tell what type of time function we have with this Laplace transformation. So here our question is, what is f of t? And by f of t, I mean the inverse Laplace transformation of capital F of s. I will show the inverse Laplace transformation like this, the letter L representing Laplace transformation to the power minus 1. It is going to be inverse Laplace transformation of capital F of s. This is question mark. So the tool that we're going to be using for taking inverse Laplace transformation is called partial fraction expansion. And it is nothing but writing this complex Laplace transformation in terms of simpler Laplace transformations whose inverse Laplace transforms we know. So here I have an s term here, an s plus 2 term. Remember, 1 over s is the unit step function, and 1 over s plus 2 is e to the minus 2t. So if I can write this function as a linear combination of 1 over s and 1 over s plus 2, then I will know what the inverse Laplace transformation would be by using the linearity property of the Laplace transformation. So here let us try to use partial fraction expansion. I haven't taught you what partial fraction expansion is, but this is going to be quite simple. But then we're going to see the general theory. So I have f of s. I will try to write this thing, s plus 2, as a linear combination of 1 over s and 1 over s plus 2. So this is going to be a over s plus b over s plus 2. In general, we won't put just constants here at the numerators of these pole factors here. But here, because these pole factors are first order, I am going to be putting constants here. In general, we will put polynomials with larger order into the numerators when I have higher order polynomials in the denominator. But here, in the denominators, I have only first order polynomials, which means that I need to put here a zeroth order polynomial, which is a constant. And this is first order, so I'm going to put here a zeroth order polynomial, which is a constant again. So I want this equality to be satisfied for all s's. So what I'm going to do is to equate the denominators of both terms. So I'm going to multiply the first term with s plus 2, and I'm going to multiply the second term with s, and then the denominator is going to be the same as the left-hand side. Okay? And if I actually take the s parentheses here, it's going to be a plus b times s plus 2a divided by s plus 2. Now what I have to do is to choose the constants, unknown constants a and b, such that the numerators of these two Laplace transforms are also equal. Okay, for all s values. And we see actually how to equate the numerators. I'm just going to be equating the coefficients of this polynomial to the coefficients of this polynomial here. All right? So coefficient of 1 here is going to be just 2a. So I have 2a is equal to 1. And coefficient of s here is a plus b. Coefficient of s here is 1. So a plus b is going to be 1 as well. All right? If I solve these two equations for a and b, a is going to be 1 over 2, and b is going to be 1 over 2 as well. So what does this mean? This means that f of s, which is this complicated function, it is not very complicated, but it's more complicated than what we have seen before. It is going to be 1 over 2 times a times 1 over s plus b times 1 over s plus 2. Both a and b are 1 over 2. Now I can actually use the linearity property of the Laplace transformation in order to be able to take the inverse Laplace transform of this function. So inverse Laplace transform of 1 over s is going to be just 1. It is the unit step function. And inverse Laplace transformation of 1 over s plus 2 is going to be e to the minus 2t. Okay, so here we see that there is an a here, so this is e to the at, and there is minus a. So this is plus 2, so this should be minus a, then a is minus 2. Okay, so I will have e to the minus 2t. Now I can write my f of t. It is equal to 1 over 2 times 1, which is the unit step function, plus 1 over 2 e to the minus 2t, and this is true for t larger than or equal to 0. So we solve this question by using partial fraction expansion. And the procedure is going to be more or less the same for all Laplace transformations. We are going to be concentrating on the denominator, and then we are going to expand the function in terms of its partial fractions, which are these two terms, and with some unknown coefficients here. Then we will equate the denominators, and then we will solve for the unknown coefficients to equate the numerators of both Laplace transforms. Okay? So now let us see the general theory. So partial fraction expansion. In general, we are going to have a Laplace transform that is looking like this. F of s is, in the denominator, I will have an nth order polynomial, a1 s to the n minus 1, going until an. And in the numerator, I am going to have a polynomial which is in general having a smaller order than the denominator polynomial. So in the numerator, I would have something like this: b1 s to the n minus 1 plus b2 s to the n minus 2, going until bn here. So we will concentrate on the denominator here. It is d of s. And we are going to try to write d of s in terms of its factors. So here the numerator, as you see here, I can have, in the numerator, I can have a polynomial with an order smaller than, strictly smaller than n. And the order of the polynomial in the numerator does not have to be n minus 1. If b1 is equal to 0, then the order is going to be, and if b2 is non-zero, the order is going to be n minus 2. And if both b1 and b2 are 0, and if b3 is non-zero, then the order of the numerator is going to be n minus 3, etc. And if all these coefficients are 0 except for bn, then we're going to have a constant in the numerator. Okay, a zeroth order polynomial. A constant is a zeroth order polynomial. Why is that? Because bn is bn times s to the power 0. S to the power 0 is 1, so bn is equal to bn. So a constant is a zeroth order polynomial. So here I have to emphasize one thing about these coefficients, a1 to an, b1 to bn. In this course, we will be considering some Laplace transforms of some physical signals. So the signal, for example, this is going to be the Laplace transform of, for example, a velocity signal or a position signal or a current. It is going to be an electrical current or an electrical voltage, etc. So what this means is that these coefficients would always be real coefficients. Okay? They won't be complex coefficients. So here I can say that b1 to bn are real and a1 to an are real. Okay? When you have a real coefficient polynomial, when you have a polynomial with real coefficients, like we do here, so both the numerator and the denominator are real coefficient polynomials, then those polynomials have a very specific property. If such a polynomial has a complex root, then the complex conjugate of that root is also going to be a root. Okay? So for a real coefficient polynomial, the complex roots are always going to come in complex conjugates. All right. So if you have a root at s equals to sigma plus j omega, then we will have another root of the same polynomial, which is the complex conjugate of this, the complex root here. Okay? So complex roots will always come in pairs for a real coefficient polynomial. As a result, when we have a complex pole, we always know that its complex conjugate is also going to be a pole. It is the same is true for the zeros as well. So here, what polynomial have these roots? I have to think about this. So I have to write s minus the first pole and s minus the second pole minus j omega. Okay? So this second order polynomial will have roots sigma plus j omega and sigma minus j omega. All right? So you see that in order to be able to obtain this polynomial, which is going to be a real coefficient second order polynomial, I need to multiply the complex numbers and I need to make cancellations, etc. So in general, I really do not deal with those. Instead of that, I will write this polynomial directly like this. S minus sigma square plus omega square. There is going to be an equality between these two second order polynomials, okay? So if you expand this multiplication, you're going to end up with this polynomial, okay? And the roots of this polynomial are these two, all right? How can I see that? I can just equate the result to 0. If I equate the result of the multiplication here, it is clear that the roots should be these two. Okay, either this one is 0 or this term is 0 or this term is 0, which would give me these two roots. But what about this, the polynomial at the bottom here? What are the roots of this polynomial? It's going to be the same. Why is that? So let us try to extract s from this equality. S minus sigma square is equal to minus omega square, and if I take the square root of both sides, I would get s minus sigma is equal to plus minus j omega, and if I take the sigma to the other side, s is going to be sigma plus minus j omega. Okay? So you see that these two polynomials are exactly equal. So when we have complex roots, we will always have a factor of the denominator, which is going to be looking like this. All right? When we have complex poles, the denominator is always going to have a factor which would be looking like this. And the sigma here is going to be the real part of those complex poles, and omega is going to be the imaginary part of the complex poles. So now when I start with a d of s in this form, let us try to write what type of terms we can have. So this is s to the n plus a1 s to the n minus 1 going until an. Now what type of factors I can have for such a polynomial? I will write these factors as follows. There might be a real root, there might be a real pole which looks like this, s minus lambda 1. In that case, lambda 1 is just a pole of this Laplace transformation. But of course, such poles can be repeated, okay? So what does that mean? That means that I can have a real pole like this, and it can have some multiplicity, okay? I have n1 poles exactly at the same position, s equals to lambda 2, okay? I can factor such a polynomial, or factors of such a polynomial can be a real pole, this is s equals to lambda 1, with multiplicity 1, only a single pole, single real pole at lambda 1, and there can be multiple poles at a real value. And this is S equals to lambda 2 with multiplicity M1. What are the factors? So these are representing real poles. Of course, this one is a special case of this one, okay? Because if I choose M1 equals to 1, this term would be looking like this term, okay? So in general, I have any real pole with some multiplicity. And what about the complex poles? There might be a single complex conjugate pair. So this is going to be S minus sigma 1 square plus omega 1 square. This is poles at sigma 1 plus minus j omega 1, and these poles have single multiplicity. There is a single pole at sigma 1 plus j omega 1, and there is another single pole at sigma 1 minus j omega 1. Okay? And what can happen is that complex poles can have a multiplicity which is larger than 1. Okay? So I will be representing this like this. S minus sigma 2 square plus omega 2 square, and this complex pole term, this represents the complex conjugate poles, might have multiplicity M2. And in that case, at each complex location, I will have M2 poles exactly at the same position. Okay? So in general, our D of S would be looking like such a multiplication. Of course, some of the terms can be missing. There might not be, for example, a real term, or any real term. We might not have these terms, or we might not have any complex poles for a D. So this depends on the D that we are working with. But in general, the terms that we will be working with would be looking like this. Of course, in order to have equality here, this order of this polynomial n should be the sum of the orders of each of these terms. Okay? So I will have here 1 plus m1 plus 2 plus 2m2 is going to be equal to n. If I have such an equality, then the power here is going to be equal to the largest power of s in the polynomial below. Okay? So in general, we're going to have this type of terms. And how can we actually make a partial fraction expansion if d of s is in this form? Okay? Let us try to see. So if I go back to the earlier example, in the earlier example, I have the denominator s times s plus 2. In that case, I would have two real poles with multiplicity 1. Okay? A term like this, and another term like this. And lambda 1, so m1 is equal to 1 is going to give this type of multiplication, and I won't have any complex poles. So in that example, I had m1 is equal to 1, and lambda 1 was 0, and lambda 2 was minus 2. Okay? So when I have such a d of s, then the partial fraction expansion of this f of s would be looking like this. So I will write f of s here. I will always write the factors here in the denominator. The first term is going to be s minus lambda 1. And what I am going to put into the denominator is going to depend on the order of the denominator polynomial. Okay? So here, the order of the polynomial I put into the numerator is going to be always 1 less than the order of the denominator polynomial. The order of the denominator polynomial here is 1. This is a first order polynomial. So the polynomial that I should put into the numerator is going to be 1 less than the order of the denominator. So therefore the order of the polynomial I should put into the numerator is going to be just 0. A 0th order polynomial is nothing but a constant. So I will put that constant here. A, it is going to be unknown. Just as we did in the earlier example. S is a first order polynomial, so I put a constant here. Okay? Plus, the second term in the partial fraction expansion is going to be s minus lambda 2 to the power m1. So what I told you is that I'm going to put here an unknown polynomial, and the order of this unknown polynomial is always going to be one less than the order of the denominator polynomial. What is the order of the denominator polynomial? The highest power of s in the denominator is going to be s to the power m1. Okay? So what I'm going to do is that I'm going to put here a polynomial with order m minus 1. So I will put an unknown coefficient b1 s to the m1 minus 1 plus b2 s to the m1 minus 2. I don't know what m1 is, but I'm going to always start with m1 minus 1 here, and I'm going to continue until I reach a constant, and that constant is going to be bm1. Okay? So there will always be the unknown coefficients. The number of unknown coefficients in the numerator polynomial would always be equal to the denominator order of the denominator polynomial. So here there are m1 unknown coefficients, and the order of the denominator is just m1 here. Okay? So this is the second term, the partial fraction corresponding to this term in d of s. And then I will continue with the third term. Into the denominator, I'm going to write s minus sigma 1 square plus omega 1 square. And into the numerator, I should always put a polynomial with order 1 less than the denominator polynomial. What is the order of the denominator polynomial here? The highest power of s here is s square. Therefore, into the numerator, I need to put here a polynomial with order 1, 2 minus 1, 1. Okay? So that is going to be c1 times s plus c2. And as you see here, I have two unknown coefficients here, and these coefficients, the number of these coefficients is equal to the order of the denominator polynomial is 2. I'm going to continue with the last term here, and this last term I'm going to be adding it here at the bottom. Is it visible in the video? Yes, yes. I hope so. So here into the denominator, I'm going to be writing s minus sigma 2 square plus omega 2 square. And this has the multiplicity m2. Okay? And into the numerator, I need to put a polynomial with order 1 less than the denominator order. What is the denominator order? The largest power of s here is s square, and this also have the power m2. So as a result, the order of the denominator polynomial here is 2m2. Okay? So I need to put here the first coefficients d1 is going to have the multiplier s to the power 2m1 minus 1 plus d2 as 2m1 minus 2, and these are going to continue until what? I need to have here these are going to be 2m2, all right? Because the power here is m2, this is s square to the power m2 is going to be 2m2. So the first power here is going to be 2m2 minus 1, then 2m2 minus 2. This is going to continue until a constant. And what is going to be the subscript of that constant? I need to know the number of unknown coefficients here will be equal to the order of the denominator, which is 2m2. Therefore, I need to have 2m2 unknown coefficients, d1, d2. These are going to continue until 2m2. All right? So this is what partial fraction expansion looks like for general terms like this. Okay, if you have multiple of such terms, then you need to repeat this procedure for each term. If you have, for example, s minus lambda 3 somewhere to the power 1, you're going to add a term for that just like this. All right? And that is what we did actually here in this earlier example. I had s and s plus 2, so I added a term like this for the first one and the second one as well. So we're going to expand this f of s in this form. So I start with a complicated Laplace transform, then I expand it in terms of some simpler functions. These simpler functions are called partial fractions of that complicated function. And then what we're going to do? So if this is step 1, so that is, let us say that this is step 1 of partial fraction expansion. We're going to write f of s in terms of its partial fraction expansion. What is step 2? It is going to be equating the denominators. So we are going to equate the denominators here, and we are going to get the denominator of each term equal to this function. Obviously, I will not be able to do it with this abstract function here. I need to have a specific one. But what we are going to do is simple. I'm going to multiply both the numerator and the denominator of the first term with this one, this denominator, and this denominator to make the denominator equal to this long function. And I'm going to multiply the denominator and the numerator of the second function with this denominator and this denominator and this denominator. So I will equate the denominators, and I will get a complicated numerator here at the end. Okay? Step 3, solve for the unknown coefficients by equating the numerator polynomials. Okay, we are going to solve for the unknown coefficients a, b1, b2 going until bm1, c1, c2, and d1 to d2, m2. Okay? And that is going to make us complete the partial fraction expansion. So this is how we do partial fraction expansion. And in order to be able to take the inverse Laplace transformation, then I have to take the inverse Laplace transformation of each term here. So taking the inverse Laplace transformation of such a term is easy. But taking the inverse Laplace transformation in this form, it's going to be more difficult. And even more difficult is this type of term. So now we're going to start solving some more complicated examples. So let us start with f of s is equal to s plus 1 and s plus 2 square. So here in this case we are like this. So we have the first term s, lambda 1 is 0, and the second term is lambda 2 is equal to minus 2, and m1 is just equal to 2. Okay? We have to take the inverse Laplace transformation. The question is, what is f of t? So now let us apply inverse Laplace transformation. But before we try to take the inverse, I'm first going to be making a pole zero plot here. It is not important, the zeros are not going to be important, but I will have So what are the effects of zeros here? So do you think that zeros affect the inverse Laplace transformation in any way? Yes, actually, the answer is yes. And zeros do not affect the denominators of these terms here, but zeros are going to affect these coefficients. The A is going to depend on the numerator polynomial here, and B1, B2, Bm1, and all of these unknown coefficients will be determined by the zeros of the Laplace transformation. Okay, so the effects of the poles, they determine the denominators of the partial fraction expansion, and zeros determine the numerators of partial fractions. All right, the unknown coefficients of the partial fractions. And in this example, we have a pole at s equals to 0, and we have double poles, repeated poles at s equals to -2. Okay? And we have a 0 at s equals to -1. So, if you watched the earlier lectures, you might remember what type of terms, time functions we would get for this case. And a pole at 0, it is going to mean a single pole at 0 is going to mean a constant. It is just like a constant in time domain, and it's 1 over s in Laplace domain. Okay? And double poles at s equals to -2, what would they represent? Remember the properties of the Laplace transformation that we have seen. What property was actually related to the multiplicity of the poles here? Remember, if you multiply a time function with t, then we were taking the derivative in the Laplace domain. And taking derivative in the Laplace domain was giving us multiple poles at the same location. So if I had only a single pole at s equals to -2, then I would have an exponential term, e to the -2t. But since I have double poles at exactly the same position, I will also have an additional term, t times e to the -2t. Okay? So we will see how those terms are going to appear, actually. But let us first apply partial fraction expansion. F of s is going to be equal to, I will first write s here. This is a first order polynomial, so I need to put a 0th order polynomial here, which is going to be a. Plus, I will have s plus 2 square, and this is a second order polynomial. As a result, the polynomial that I should put into the numerator is going to be first order. So I will put this polynomial as bs plus c. Okay? Then I will equate the denominators. So I will multiply this one with s plus 2 square, and I will multiply this one with s. So I have a times s plus 2 square plus s times bs plus c divided by s plus 2 square. This is the equating the denominators part. And then let us calculate the numerator here. A times s plus 2 square is s square plus 4s plus 4, plus I would have bs square plus cs divided by s plus 2 square. Let us now try to group the numerator terms here. The coefficient of s square is going to be a plus b s square plus coefficient of s. It is going, one term is here and one term is here. It is going to be 4a plus cs plus coefficient of 1, coefficient of s to the power 0. It is going to be just 4a divided by the same denominator. Now I'm ready to equate the numerators. So I have this polynomial in the numerator on the right hand side, and I have this polynomial on the numerator on the left hand side. Then what I have to do is just equate the coefficients of this polynomial to that polynomial. You see that this polynomial doesn't have any s squared term. but this one has s squared term. What does that mean? That means that the coefficient of s squared here is 0. Okay? So coefficient of s squared here should be 0 as well. So I have here coefficient of 1 is 1. So I have 4a is equal to 1. And coefficient of s is 1. So 4a plus c is equal to 1. And finally, I have coefficient of s squared is 0 here. And as a result, a plus b, which is the coefficient of s squared here, should be equal to 0. So this gives me a equals to 1 over 4. And if you try to solve for c here, you see that c is equal to 0. And b is going to be minus 1 over 4. Okay? So now I have to substitute these numbers into my partial fraction expansion. Okay? If I do that substitution, f of s is going to be a over s. A is 1 over 4. 1 over 4 times 1 over s. Plus, I have b is equal to minus 1 over 4. Minus 1 over 4 times, so here I have here this term. B is minus 1 over 4 and c is 0. So I will just have minus 1 over 4 times s divided by s plus 2 squared. Okay? So I have these terms, and I have to take the inverse Laplace transformation of these partial fractions. So you see here, the first term is easy, 1 over s. Inverse Laplace transformation of that is just 1. It is the unit step function. But this is more difficult. Okay? So let us think about e to the at. E to the at had the Laplace transformation 1 over s minus a. Okay? And what about t times e to the at? In this case, this is going to be something unknown now, but you might remember the last lecture. If I multiply a function with t, the resulting Laplace transformation is always going to be minus d over ds f of s. So f of t has a Laplace transformation capital F of s, and the Laplace transformation of t f of t is going to be negative derivative with respect to s of f of s. Okay? Now let us quickly use this property in order to be able to calculate the Laplace transformation of t e to the at. I need to take the derivative of this term. It is going to be 1 over s minus a squared. There is going to be a minus here, but that minus is going to be cancelled with this minus. Okay? When I take the derivative of this term with respect to s, it's going to be minus 1 over s minus a squared. Okay? But in front of this, there is going to be a minus 1 as well. That minus is going to cancel this minus. So I would have the Laplace transformation of t e to the at given in this form. So this is good here. So I have e to the minus 2t is going to have the Laplace transformation 1 over s plus 2. If I substitute a is equal to minus 2 here, I would have s plus 2 here. And t times e to the minus 2t is going to be, substitute a equals to minus 2 here, 1 over s plus 2 squared. Okay? So this is really nice. This gives us an idea about what the inverse Laplace transformation of such a term would be. But still, I don't have the exact correspondence between these two and this one. The good point here is that this complicated term can be written as a linear combination of this one and this one here. How can I do that? So I have s over s plus 2 squared. This is easily, you can easily see that this is equal to s plus 2 minus 2 divided by s plus 2 squared. Okay? So you see that I have created an s plus 2 here, which is going to cancel one of the s plus 2's here. S plus 2 over s plus 2 square minus 2 over s plus 2 square. Okay? So here I cancel one of the s plus 2 here with one of the s plus 2's in the denominator. It will give me 1 over s plus 2 minus 2 over s plus 2 square. So you see that this complicated Laplace transformation can be written as a linear combination of these basic Laplace transformations here. So now I'm ready to invert both of these terms. F of t is going to be 1 over 4 times the inverse Laplace transformation of 1 over s. This is just going to be a constant term, unit step function. And I have minus 1 over 4 here, an inverse Laplace transformation of this thing. And it's going to be here 1 over s plus 2. It is e to the minus 2t and minus 2 times 1 over s plus 2 square. It is t e to the minus 2t. Okay? Then I can actually simplify this a little bit by taking e to the minus t parentheses. So it would be 1 minus 2t e to the minus 2t. Okay? So this completes this example. So you see that what happened, here. So I had a term s plus 2 square in the denominator, and this s plus 2 square, which is a double pole at s equals to minus 2, it brought not only t e to the minus 2t, but it brought as well also e to the minus 2t. Okay? This is always happening actually in Laplace transforms. If you have a second order term, you can sometimes get only this term, or sometimes, depending on the numerator here, you might also get the expression here without t's. All right? If this was cube, then I would have t square e to the minus 2t, and there might be a term t e to the minus 2t, and there might be a term just e to the minus 2t like this. So when we have a higher order term like this, we might, in many cases, have some lower order t terms here as well. So we don't always get t e to the minus 2t only. Sometimes we get the lower order t multiplications here as well. So let us solve one more example. This example is going to be simple, and I'm not going to finish it completely actually. I will leave some parts as an exercise. So this is the example, and we have to take the inverse Laplace transformation of this term. So here, the first thing that you have to do here is to look at the pole locations. Whether the pole locations are real or they are complex or not. The discriminant here is going to be b squared minus 4ac, and it is going to be just 4 minus 4 times a times c. It is times 3, it's going to be 16. Okay? Discriminant is positive here. That means that we are going to have 2 real poles. Okay? And what are those 2 real poles? I can actually write this. You can calculate the poles from the discriminant, but I won't do it here. It is easy to see that they are going to be at s plus 3 and s minus 1. Okay? So where are the pole locations? Poles are at s equals to -3 and s equals to 1. All right? Now if I make a pole 0 plot here, it is really easy. Maybe I don't have to do it. Imaginary s. So at s equals to 1 and at s equals to -3, I have my poles. What type of terms are these going to bring into the time function? Of course, these are exponentials. 1 over s plus 3 is an exponential. 1 over s minus 1 is an exponential. This is going to be 1 over s minus 1 is going to be e to the t, and 1 over s plus 3 is going to be e to the minus 3t. Okay? So if I make a partial fraction expansion here, I would have s plus 3 plus b s minus 1. Then you need to equate the denominators to calculate what a and b are. And then if you take the inverse Laplace transformation, you're going to have a times e to the minus 3t plus b times e to the t here. This is true for positive, non-negative t values. So here, as an exercise, I leave to you, find a and b. It's really simple. But you see that you shouldn't think that you have sines and cosines immediately when you see an s squared term there. So you might have just two real poles, which is going to mean that you're going to have two different exponentials. Okay? Let us solve another example. In this case, we are going to have something similar, only a sign change. So it is 2 over s squared plus 2s plus 3. The task is always the same in this lecture. Take the inverse Laplace transformation. So here again, I'm going to be interested in the pole locations. So the discriminant in this case is 4 minus 12. It's going to be minus 8. Okay? And if I calculate the pole locations here, S12 is going to be minus b plus minus square root discriminant divided by 2a. And this is going to be minus 2 plus minus square root of minus 8. It is 2 square root 2j because of the minus 1 here, divided by 2 here. So we have minus 1 plus minus square root 2j. Okay? Of course, you can find the poles in an easier way. In general, I don't try to use such an approach. What I do instead, which is also useful to be able to take the inverse Laplace transformation, is to complete this denominator into a full square. Okay? So if you do it like that, then you will be able to obtain the pole locations, as well as you will understand what the inverse Laplace transformation would be looking like here. But first of all, I will make a pole 0 plot here. So the real parts of the poles are at minus 1, and the imaginary parts are at square root 2j and minus square root 2j. Okay? So the pole locations are here. Now remember the last lecture. When you have poles in the open left-half plane, this means that we are going to have a decaying function as time goes to infinity. And when we have poles with non-zero imaginary parts, when we have complex poles, that means oscillations of sine and cosine type. And the exponential decay is going to be determined by the real parts of the poles, and the frequency of the oscillations is going to be determined by the imaginary parts of the poles. So the frequency of the oscillation here going to be is square root 2 radians per second. So I will have cosine square root 2t and sine square root 2t coming from the imaginary parts. And due to the real part here, which is -1, I will have in the front of those sines and cosines, I will have an e to the minus t, which is decaying exponentially as time goes to infinity. Okay? So by just knowing the poles, you can actually see what type of terms you are going to get in the inverse Laplace transformation. So as I told you, I'm going to complete the denominator here into a full square in order to be able to take the inverse Laplace transformation. Here, when we have complex poles, I never try to separate. I never try to make a partial fraction expansion to such a term. Okay? Of course, this term is nothing but 2 over s plus 1 plus square root 2j and s plus 1 minus square root 2j. Okay? I can separate this Laplace transformation into two parts like this, into its two roots like this, and then I can try to make a partial fraction expansion. We never do that. We always keep this polynomial as itself. So don't do this. All right. Of course, you can actually find the actual solution using making a partial fraction expansion like this, but it's more difficult than working with this polynomial directly here. Okay? This is a valid way to take the inverse Laplace transformation, applying a partial fraction expansion to such a term. But then you're going to get complex a and b factors, and at the end, those a and b factors, their complex parts are going to cancel, but you will probably make a calculation mistake if you try to do it by applying partial fraction expansion to such a term like this. So instead, using this polynomial directly here is easier. So f of s, I can actually try to write this polynomial like this. S squared plus 2s. So suppose that I would like to complete these two terms into a full square. Okay? If I want to complete these two terms into a full square, you know what to do. Divide this coefficient by 2 and add the square of it to the right of this one. So I will add just the 1 here. This is s plus 1 square. Okay? But this is not the same as that one. So I have plus 3 there. So I will just add 1, 2 here. Okay, which makes these two Laplace transformations the same. But I can actually write this one as s plus 1 square plus 2. So now why is this giving results in an easier way? First of all, I can actually look at the pole locations from this equation directly. S plus 1 square plus 2 equals to 0. It gives me the pole locations -1 plus minus j square root 2. The same as what we did here. And this is also going to make things easier for us, because here you see that the denominator is a full square plus a constant. Okay? This is really looking like a sine and cosine function Laplace transforms in some way. Remember, sine omega t had the Laplace transformation omega over s squared plus omega squared. And cosine omega t had the Laplace transformation s over s squared plus omega squared. Okay? So here you see the denominators, the similarity of this one to these two. There is some similarity, but they are not exactly the same. So instead of s here, I have s plus 1 here. Okay? So how do I handle such an s plus term? In order to be able to handle that, I will remember one of the properties of the Laplace transformation. If you have a function f of t, and if it has a Laplace transformation f of s, when you multiply that function with e to the minus at, then the Laplace transformation of the new function happens to be f of s plus a. Okay? This is the property that we're going to use to be able to take the inverse Laplace transformation here. So if sine omega t is given like this, then e to the minus, here I have s plus 1, so I will have e to the minus t here. Sine omega t is going to have the Laplace transformation. Instead of s, I will substitute s plus 1. So I have s plus 1 square plus omega square here. And e to the minus t cosine omega t is going to have, instead of s, I will substitute s plus 1. S plus 1 over s plus 1 square plus omega square. Now I can actually try to invert this Laplace transformation here. So which one is this looking like? This one or this one? This one or this one? It is looking like the sine, right? So here I see that in the cosine I have an s term in the numerator. So here I don't have any s term, but I have a constant. So it is looking like this Laplace transformation. So now I have here f of t is going to be, I won't write f of t directly, but first I will try to convert this one into a Laplace transformation of that one. So f of s is, in the denominator I have s plus 1 square plus 2. This 2 is the omega square, okay? It is omega square. So what is omega here? Omega is going to be square root 2. In the numerator, I have just 2 here, but in the numerator here, I need to have square root 2. Okay? So I'm just going to write that 2 as square root 2 times square root 2. Okay? Then this thing is something that I can take the inverse Laplace transformation. So here, f of t, so this is omega over s plus 1 square plus omega square. Okay? This is going to be square root 2, it is this multiplication here, times the inverse Laplace transformation of this term. And it's going to be e to the minus t times sine omega is square root 2 t here. So you see here that when I have a poles at these complex locations, the real part determines this factor in the exponential. This is e to the minus 1 times t. Okay? That minus 1 is coming from the real parts of these poles. It is determining, the real part is determining the decay rate of the oscillation here. If instead of minus 1, if I had plus 2, for example, then I would have here e to the plus 2t. In that case, the sign would be growing because the poles are in the right half plane. If instead of minus 1 real part, if the poles were here, then the exponential factor would be 0 because the real part would be 0 on this line, imaginary axis. So it would be then e to the 0t, which is just 1. So I would have a pure sinusoid, which is not growing, not decaying, etc. So if the poles are in the left half plane, those terms will be decaying. If the poles are in the right half plane, those terms would be growing. If the poles are on the imaginary axis, there would be neither a growth nor a decay. Okay? So this factor of the exponential, the power of the exponential, the factor in the power of t is going to be determined by the real part of the poles. And the frequency of the oscillations, the frequency of the sine and cosine functions will be determined by the imaginary parts. Okay? And this is here square root 2 is determined by the imaginary parts. All right? So let us solve one more example. As you see in this lecture, I'm again forgetting constantly this t larger than or equal to 0. So before time t equals to 0, this function is going to be 0, and this is only valid for non-negative t instance. So this example is going to be like this. F of s is looking like this. So it is s squared plus 2s plus 3. So I just added an s term here in the front. So now let us try to apply partial fraction expansion here. So I have a over s plus, I know that this polynomial is exactly the same as the ones before. So it has complex roots at -1 plus minus square root 2j. And as a result, I would keep it as itself. Okay? I won't make any decomposition of it into its complex roots. So I would have s squared plus 2s plus 3. If there were multiple real roots of this polynomial, then I would separate it into its partial fraction expansions as well. There would be multiple exponentials coming from each of them. So I would have here, this is a second order polynomial. As a result, into the numerator, I'm going to put a first order polynomial, one less than the order of the denominator. So it is bs plus c here. Okay? So now let us equate the denominators. So I would have here, this is equal to a times s squared plus 2s plus 3 plus s times bs plus c. bs squared plus cs divided by s squared plus 2s plus 3. So now let us calculate the coefficient of s squared. It is going to be a plus b times s squared plus coefficient of s is going to be 2a plus c, and coefficient of s to the 0, which is 1, coefficient of 1 is going to be 3a divided by s squared plus 2s plus 3. Now what I'm going to do is just equate the numerators. So you see that there is only a constant term here in the numerator. So what does this mean? This means that coefficients of s and coefficient of s squared are going to be 0. So a plus b is equal to 0. 2a plus c is equal to 0. Coefficients of s squared, s, are 0. And coefficient of 1 is 3a is equal to 2. Okay? So from this last equation, I can solve a equals to 2 over 3. So b is going to be equal to minus 2 over 3. And c is going to be equal to minus 4 over 3. Okay? Let us substitute these coefficients back into the partial fraction expansion. So in that case, f of s is going to be, I have 2 over 3 times 1 over s, and b is minus 2 over 3 here, and c is minus 4 over 3. As a result, here I can take minus 2 over 3 parentheses, and here I would have s plus, instead of c, in minus 2 over 3 parentheses, this is going to be 2. Okay? And I will just write this denominator in that full square form. Okay? S plus 1 square plus 2. So now these are the only partial fraction expansion steps that I have to apply. Then now I have to take the inverse Laplace transformation of each term. Obviously you see here that taking the inverse Laplace transformation of this term is much easier than taking the inverse of this one. Okay? Inverse of this one is more difficult. Why is that? Because here the numerator does not look like this one or this one here. Okay? It is not looking like these two. It's not looking like these two here. But how can I actually invert such a Laplace transformation? S plus 2 over S plus 1 square plus 2. Let us go back to these terms. So here in the e to the minus t cosine omega t, I have s plus 1 here. Okay? This s plus 1 should be the same as this s plus 1 here. In the numerator and the denominator, I need to have the same factor. On the other hand, in the sine, I don't have such a requirement. But I can actually try to write this Laplace transformation, which doesn't look like any of these. I can try to write this one as a linear combination of these two. Okay? How can I do that? I can do it like this. So instead of writing s plus 2 here, I will write it at s plus 1 plus 1. Okay? S plus 1 square plus 2. And then I will separate the s plus 1 part. S plus 1 square plus 2 plus I have 1 over s plus 1 square plus 2. Now you see that the inverse of this part is easy. Okay? Because here it is just looking like this. So inverse of this part is going to be e to the minus t, because of this plus 1 here, times cosine square root 2t. What about this part? This part is going to be a sine function, but in the sine function you see that there should be an omega factor here. Okay? So in the sine function, we always have the square root of this constant term here in the numerator. Here, the constant term in the numerator is 2, so there needs to be a square root 2 here. But this is not the correct Laplace transformation, so I'm multiplying with 1 over square root 2 as well. So now this thing is nothing but e to the minus t sine square root 2t. And I need to multiply it with 1 over square root 2. So now I'm ready to take the inverse Laplace transformation. So f of t is going to be, I will have a constant term coming from this. It is 2 over 3 minus 2 over 3 in 2 over 3 parentheses. I would have this thing, e to the minus t times cosine square root 2t, and I would have this term plus 1 over square root 2. I take this multiplier first, and then I have e to the minus t sine square root 2t. Okay? So you see that a term, when I have s's here, some s terms here, we're going to have sine and cosine at the same time. But you have to be very careful here in writing such a term as a linear combination of these two terms here. You have to be careful, but it is nothing more difficult than what you can do. So these are completing my examples. The last thing that I'm going to do here is to work on a hypothetical problem. Okay? So I have f of s. Let me say that I have a hypothetical problem where I have an s square here, and I have s plus 2, s minus 4 cubed, s squared plus 9, Thanks to God, this is an hypothetical example. So s minus 2 square plus 4 square. Okay. Suppose that I have such a Laplace transformation, and suppose that I would like to take the inverse Laplace transformation of this, and I don't know what the denominator, I don't care what the denominator is. What I care here is what the time function would be looking like in this case. That is the only thing that I care here in this hypothetical example. Okay? First thing, I'm going to make a pole zero plot. You don't have to do this, but for me to explain, it is clearer to work with a pole zero plot here. So I have here s squared, double poles at the origin. These are real poles. And a single pole at s equals to minus 2. This is an exponential. You know it's a decaying exponential. It's on the left half plane. And I have s minus 4 cubed. So I have a real pole here at 4, but there are triple poles at the same location. Okay? And I have purely imaginary poles at plus minus 3j. And I have repeated poles at 2 plus minus 2j. Okay? So this is the point, let us say 2. This is the 4 plus minus 2j. This is 2j and minus 2j. I have poles here, but they're repeated twice. Okay? So I have double poles here. So this is my pole zero diagram. It's quite complicated, but this gives me the idea of what type of time functions I'm going to have in the inverse Laplace transformation here. So the first thing, I will go in the order that I write these terms here. F of t is going to have the following terms. There is an s square here. Okay, so this is first of all, let us try to make a partial fraction expansion. F of s is, I have s squared, so I will put here a1s plus a2, a first order polynomial, because this is a second order polynomial, plus b s plus 2 plus s minus 4 cube. This is a third order polynomial. As a result, I need to put a second order polynomial into the numerator. So it is c1 s squared plus c2s plus c3. Okay? These are the unknown coefficients. And I have s squared plus 9. This is a second order polynomial with complex roots. And as a result, I put here d1s plus d2. And finally, I have s minus 2 squared plus 4 here. This is, and there is a square here. This is a fourth order polynomial. As a result, I need to put here a third order polynomial. Okay? So it's going to be e1s cubed plus e2s squared, e3s plus e4. Okay? So this is the partial fraction expansion of this function. Now I'm going to try to write the time functions corresponding to each of these terms. All right? So now you see here, when I find a1, then I would have that multiplied by 1 over s. Okay? This is going to be a1 times 1 over s plus a2 times 1 over s squared. Okay? So I would have here a1, a constant, a1 over s, plus a2 times 1 over s squared. 1 over s squared is the ramp function. It is t. So you see here again the same thing. When you have a second order term with repeated poles, I get a t multiplication, but also the original term, the lower order polynomial multiplications. Okay? And let us write the other terms. B times e to the minus 2t. This is like this. And now comes the more complicated terms. So I have a repeated pole at s equals to 4. This is going to bring me e to the 4t, but there is a cubic order here, okay? When you have repeated poles, you're going to see that you will have e to the 4t. Since this is repeated 3 times, then I would have a t-square multiplication, and of course there will be some coefficient in the front, plus c1 prime. This c1 prime does not really have to be equal to this c1 in general, okay? Plus c2 prime. When you have a t-square multiplication, you're going to have lower order multiplications because of this repetition. What happened in the s square is going to happen most probably with s minus 4 cube. Okay? So I have t-square multiplication, but lower order multiples would also be possible in this case. So plus c3 prime times e to the 40. So due to the triple multiplication here, so the triple order of this pole, I put a t-square in front of e to the 40, okay? But I also add these terms as well. These terms might also be possible. For some numerators, these type of terms would also appear in the inverse Laplace transformation. But for some, if you are lucky, sometimes these coefficients might be equal to 0, and these terms might disappear. But in general, there will be terms like this in the inverse Laplace transformation. You see that when you see this multiplicity here, you are always adding one less power of t here in front of the exponential. Okay? So this is the third order. So the highest power of t that I multiply here is 2. And there is here, this multiplicity is 2. So the highest order power here that I multiply this term is with t. Sorry, maybe I have forgotten here. This is t, and I have a plus sign here. Okay, so now come back to this term. So I have d1 s over s squared plus 9. This is cosine, okay? d1 cosine 3t. Plus, do you think I will write here just d2 sine 3t? This part is d2 over s squared plus 9. Do you think I would have d2 sine 3t here? The answer is no. Sine 3t is 3 over s squared plus 9. Okay? As a result, in order for me to be able to write here this sine t, I need to divide the result by 3. Multiply this one with 3 and divide by 3, then this division is going to give me this. And what about the rest? And I have complex poles at these locations which are repeated twice. Okay? And what type of terms? Because of the repetition here, because of these 2 here, if this 2 was not here, then what would I have? In that case, I would have e to the 2t cosine 2t plus e to the 2t sine 2t. Okay? E to the 2t is coming from the real parts, and sine and cosine 2t are coming from the imaginary parts. Okay? But because of these 2 here, there is the multiplicity of these poles. I'm going to have to add a t multiplier here, and I will put here E1 prime. In general, this E1 prime does not have to be equal to this E1, and I will put here E2 prime. This does not have to be equal to E2 here. But is this all? We know that when I have multiple poles here, I am going to have the lower order polynomial multiplications as well. For s minus 4, I had the triple order pole here, and I multiply the same thing with t squared, t, and 1. Okay? I'm going to do the same thing for the complex poles as well. So in addition to these terms, there might be terms like this without the t multiplication. E3 prime e to the 2t cosine 2t plus e4 prime e to the 2t sine 2t. And these e3 prime and e4 prime in general do not have to be equal to this e3 and e4. So these are the terms that I can have in the inverse function. Of course, trying to take such an inverse would be really terrible by hand, but this is the general case that you can have in the inverse time function. So this actually completes the topics that I'm going to cover in this lecture. So in the next lecture, in the coming lectures of this week, we are going to actually go into a new topic that is called mathematical modeling. So we are going to start modeling the systems. We are going to start with some electric circuits. So fortunately, you will only need to know very simple electric circuits. So summation of the voltages is the total voltage, and the current will be the same on a single line, on a single circuit, etc. And then mechanical systems, translational and rotational systems, and we will see the so-called DC motors. I will try to give this information in a suitable way to your background, actually. So obviously I won't be able to teach like I teach an electrical engineering class in EE381, so I will try to make everything as basic as possible in this course. But that's going to be all for this lecture. Thank you for watching. Bye-bye.